Okay, everyone, welcome back to another lecture. We are on week 10, I believe, maybe rapidly moving towards week 11. I'm not really sure. However, we are going to continue our discussion with inferential data analyses, and today we are going to talk about statistical power, and we're going to be talking about effect size, and we're going to be talking about ANOVAs. So we're going to kind of move into some deeper, more complex statistical analysis methodology. And again, we're not doing this to do a deep dive into how these statistics are performed. We're just trying to give you an overview of what these statistics are, and I'm doing my best to model these statistics or make them very specific to your areas of research. So again, it's been a great learning opportunity for me, and I think I have some really good stuff for you guys today. So we are just talking about these type of statistics that you might see in your papers that you are looking through that will maybe better help you understand what these researchers are doing or what they're using to help you with your lit circles, or perhaps to help you describe a paper in your lit review. So that's all we're doing this for. And some of this stuff you might already know, and you may know it better than I do. So if you do, that is fantastic. And this will all just be review. So let's dive into today's lecture, and we'll start talking about some stats here. So we are going to start by talking about three critical factors that really influence statistical power. And these factors are sample size, which we really haven't talked about too much, but ideally, the more sample size we have, the more statistical power we have. So bigger numbers, if we have an N of 300 versus smaller numbers, an N of 3, well, we're going to have much more statistical power with a larger sample size than if we have a small sample size. And I think I gave you guys an example of this last week, where I was talking about the type of research that I do. When we're doing muscle biopsies and we're doing different sort of research that's highly, what's the word I'm looking, invasive, right? You're pulling out muscle biopsies, you're pulling out blood samples. Sometimes we're hooking them up to machines and we're running glucose measurements, and we're infusing glucose into their body, right, at a certain rate. These are really, really invasive procedures, and it's really hard to find, 300 people that want to sign up and do that type of research. So in our type of research, in the wet lab sort of translational sciences research, we don't get those N values. We get about an N value of 10, perhaps. Maybe sometimes we'll get an N value of 20, which is a really good sample size for us. But this reduces our statistical power quite a bit, where if you're doing questionnaires and you're doing maybe psychological evaluations, you could easily get an N size of 150 or 200 or 300 or 1,000, because these are not invasive procedures. So, if we have a sample size that is greater than what I get, you're definitely going to have more statistical power. So it makes it easier. Ideally, it just makes it easier to detect the differences between groups. Now, the effect size, this is something that we'll talk about with a little bit of detail today. Effect size refers to how strong or how large the difference is between two groups or two conditions. So if I have a group here, if I have group A, that's diabetic, and group B, which is lean, healthy individuals, the effect size between A and B is going to be quite distant, right? So that's going to be a really strong effect size, because anything I'm looking at in people who are diabetic is going to be vastly different than anyone that I'm looking at that's lean, healthy, and has no metabolic complications. Now, if I looked at, let's say, diabetics who was A, and individuals with certain types of cancer, which is B, look how much closer these two are to one another. Cancer and diabetes shares a lot of overlap. And because of that, the effect size might be much smaller. So you can see visually that an effect size between A and B with people who have metabolic abnormalities and people who don't have any abnormalities, that's going to be a really big effect size. But if I'm looking at people with two conditions where there's a lot of overlap, cancer and diabetes, that effect size is going to be very, very small. So we'll talk about effect size. And again, just like the n size or the sample size, the bigger the effect, the higher the power. The larger the samples, the higher the power. And that power just means we have more significant and statistical power. And then if we're looking at the significant level, the p-values, well, we've talked about this quite a bit. And this allows us to reject the null hypothesis if we're at a 0.05. And if we have a big sample size, we have a big effect size, and we have a big p-value, well, that gives us a lot of statistical power. Now, there is a little bit of a relationship between p-value and effect size. So sometimes, even if we get a significant p-value, that's not enough. We have to calculate an effect size. And I'm sure you guys are coming across papers now where they are talking about, of course, sample size. You have this many individuals. You have a p-value of this, but does that really mean anything? Is there really any big effect between sample size or samples or populations? Are there really any differences between them? Even though we have a significant p-value, is there an effect size? Is there a difference between group A and B? And how big is that difference? Now, if we look here, this is just kind of an analogy that I created to kind of show you what statistical power is. So this is a very low dim flashlight. And of course, if we have a low dim flashlight, we might miss some really important things. And this here, you see this little flashlight here, this is lighting up an entire forest. So I told you guys to think of statistical power as a flashlight. If the flashlight is dim, you have low power. Right? So if we come back here and we have low power, that's some pretty weak research. And I think we've seen that so far. I think we've been presenting on some papers that really showed kind of some low power. Where if we have a brighter flashlight, which means if we have more statistical powers, this helps us see things more clearly. It helps us see the factuality of the research we're conducting more clearly. And this here is just kind of reiterating what I just said. So again, larger sample size provide more reliable estimates, okay, increasing the likelihood of detecting a true effect. And that's what we are looking for with statistical power. If I go back here, go back. Come on, you can do it. There we go. If I have very low power, I'm not seeing a true effect, and my paper's going to be weak. But if I have high statistical power, you can see here that the true effect is very abundant and very clear. So just kind of reiterating that. So effect size, the bigger the effects, bigger effects are easier to detect. So again, if I look at diabetics and I look at lean, healthy individuals, and I look at their metabolism, and I measure things in their blood, and I measure things in their urine, and I measure things in their muscle, they're going to be vastly, vastly, vastly different. Well, one, because I have a disease state, and then two, I have a non-disease state. So that effect size is going to be massive. It's going to be really easy to see those true effects. But again, if I come back here and I have diabetes and I have cancer, there's a lot of overlap to those metabolic disturbances. So I might not have a big effect size. I might not see a true effect because there just might not be one between those types of individuals. And this is just reiterating the exact same thing, right? Group A versus Group B. What is the true effect size between the two groups that we are measuring? Is it very little? Or if these two groups were further apart, let's say I look at this individual and I look at this individual, and let's say I'm in the world of physical therapy. Let's say, oops, sorry about that. Let's say this individual had conducted a strength training regimen to repair lower back pain, and this individual conducted flexibility training to help repair and restore lower back pain. Well, those are two vastly, vastly, vastly different approaches to addressing lower back pain. And we could imagine that if we had a whole group of people doing strength training, I'm just going to put ST, and I had a whole group of individuals doing flexibility training, well, I would imagine that the effect size would be very different in lower back pain, because if we're putting load on a back that is already injured by applying weights versus non-load, and we just have people working flexibility training, I would imagine that effect size would be vastly, vastly different between those two groups. And I'm just going by my hunch that strength training is going to aggravate the spine, especially if you're putting load on the back, if you're doing any types of squats or bending, versus flexibility training, which is not going to cause any type of further aggravation to that area of the body. So again, it's just kind of saying, what is the difference? What is the difference in the effect? And I would say that people who are doing flexibility training are going to heal much, much faster than people that are doing strength training for lower back pain. So that would be a big effect size, because they're taking an approach that might just be more gentle and more therapeutic on the spine versus this group, which might be aggravating the spine. So these are just examples of what an effect size is. And I'm going to show you a couple more examples now that we've introduced it. So statistical power, when we're talking about power, once again, it is sample size, it is p-value, and it is effect size. And effect size tells us, even though there's a p-value, is it a small effect or is it a large effect? And you can start thinking about how we can apply this to your specific world of research. Okay, so why is statistical power important? So imagine we're conducting a study on mindfulness and mindfulness training, and if it reduces anxiety in athletes. And I'm going to give you some more examples of this in a moment, so I'm just kind of trying to set the stage right now. If we have a small sample size and we have a weak effect, well, your study doesn't have enough power to really detect any real difference, right? So if I go back to this, right? If I have two different groups here and I have a small sample size and I have a small effect, well, there's really not much going on here. We just wasted a lot of time, a lot of money, and a lot of effort trying to do research that really is insignificant. So on the other hand, if we have a well-powered study and it allows you to confidently say whether mindfulness training works or not, well, that's a completely different story. So in essence, having enough statistical power is crucial for providing valid and trustworthy results. It saves you from wasting a lot of time, a lot of resources, and potentially misleading conclusions. So let's talk a little more now about these differences. Oops, sorry about that. I'm just making all sorts of mistakes here. That's what I was looking for right there. So we're talking now about this effect size, and we're talking about how big is the difference between two groups or two variables, right? And this is kind of showing you right here. If I had two groups, like group A, and I'm just going to go to my world because it's just easier for me to understand these things. I had group A, which is diabetics, and I had group B, which is lean, healthy individuals. You can see here that the mean values of something that I'm measuring, okay, let's say it's blood glucose, okay, let's just say it's blood, I'm just going to write BG. It's blood glucose. You can see here that, and let's say I'm doing it at rest, you can see here that the difference between group A and group B, blood resting glucose levels, is pretty significant. You see I'm filling in this space. I'm comparing these mean values here. I'm looking at the difference between this and this, and that's showing me that there is a true effect size. Well, how strong is that effect size? I don't know, but we can calculate it. And I'm not going to talk about, we're not going to calculate in this class, but we're going to talk about why they do it. So we're talking about effect size here. So we collected data, right? I'm just kind of reviewing so we can go back to, what we've talked about in the past. We ran a statistical test or several statistical tests. We found a good p-value. So, wow, okay, we got something here. We have let's say 0.03. That's a good p-value. And now we want to tell the world what we found. We want to say, hey, we really found something here. It's really exciting. It's all about the p-value, right? So we got a good p-value, and now we can say, yep, I'm going to reject the null hypothesis. We're not going to make any of those errors. We're not going to make any of those mistakes. Things are looking pretty good, right? So the p-value tells us an effect exists. So it's saying that, okay, there is a difference between A and B, but it doesn't tell us how strong that difference is. And that's what we're looking for within an effect size. And one of the things that you might have seen is this Cohen-Dees calculation that helps us determine effect size, right? So if you're looking through a paper and you're like, what the hell is Cohen-Dees? Well, that's just saying that this group found a statistical significant difference between two groups or two variables, right? And now they're just calculating an effect size to see how strong that effect is, right? So the p-value just tells us that there is a difference, right? With diabetics, there is a difference between resting blood glucose levels with diabetics and resting blood glucose levels with lean, healthy individuals, right? And I'll even give you a value here. So let's say that diabetics have 230 milligrams of glucose per deciliter at rest, and non-diabetics have 70 milligrams of glucose per deciliter. 230 versus 70 is quite a big difference. My p-value is telling me that there is a difference between blood glucose with diabetics and blood glucose with lean, healthy individuals. But I don't know how strong that effect size is. I don't know the magnitude of that effect. So I'm going to use this calculation, which is going to compare the mean values between those two groups, and it's going to tell me if the effect is strong or if the effect is weak. So one of the most common ways that we measure effect is through this Cohen-Dees calculation, and Cohen-Dees compares the means of two groups and calculates the difference in standard deviation. So this comparison is going to take the mean values and it's going to use the standard deviation. We talked a little bit about standard deviation before, and again, I'm not asking you to calculate. I'm just asking you to understand the puzzle pieces that we're using here. So let's look at what these the effect calculations are. And let's look what the value of the results are and what they mean. So let me go to the next slide here. So if I am looking at a effect size, and I have this visual here, right? You can see that if I have the mean value of this group, and then right behind it you see another group. Let me change the color. Let's do green. And then right behind it we have green. We have this other mean value right here. Well, you can see that those two values almost overlap. So you really can't see the difference between group 1 or group A, which is black, and group B with this red, right? So those mean values are side by side. There's really not much of an effect there. So if we get a p-value of 0.05 and then we do this Cohen-Dees calculation and it tells us that, hey, there's really not much of an effect there, this is what we call a weak effect, right? And this hurts our data. We have a small effect, and a small effect is a weak effect. And when we get a calculation of a D value of 0.02, so I'm going to say 0.2, that tells us that it's a pretty weak effect, and that's going to be problems for us in our data. Now let's say I run a calculation, a Cohen-Dees calculation again, and I see that there's a medium effect. So here you can see, oops, sorry about that. You can see clearly that those two means are not overlapping. There's not a lot of difference between them, but they're not overlapping like the previous one. So let me do this one in yellow. Here's the mean value. Just kind of follow my little cute yellow pen here. And then the next group, let me get a different color. Let's do green. The next group's mean value is here, right? Now, if we look at the space between here and here, there is some distance. There is an effect size. Compared to this one, where they were right on top of each other, right? And let me go back to what I was talking about here, right? If I have a diabetic group and a cancer group, right? So this group is diabetic, this group is cancer. There is not much space between these two groups, which means that there's a lot of overlap in conditions. And even though I might see some differences, I might get a strong p-value that like 0.04. If I calculate Cohen-D's and I'm using their standard deviation and their mean value, well, it's telling me that there's not much of a difference between these two groups here. So it's a weak effect size, and you can see that they're very close to each other. So let me go back here. So now if I look at a medium or a modest effect size would be a D that is equivalent to 0.05. So that's how that would look. That's telling me that there is a difference between those mean values when we also bring into consideration the standard deviation. Now, if we look at a large effect size, well, look at the peaks here of these two curves, and we can see, of course, that there is, let me go back to yellow. If this is, let's say this is my diabetic group, right? Here's the mean value here. And then let's say that this is my lean, healthy individual group here. And let's say I'm looking at, again, let's just use blood glucose because it's easy. Well, you could see that there is a much bigger difference between those two mean values compared to this and this, which means that this is a strong effect size. And a strong effect size is 0.8 or higher. Okay, so that is what this Cohen-D kind of looks at. And I have an analogy here, and I like to use analogies just in case something's not sinking. And if we're talking about an effect size, think of an effect size as volume of music at a party. Okay, a statistically significant result tells you there is music playing. Okay, so there is a difference. Okay, so something is happening. So okay, if I look at strength training and flexibility training between group A and group B, right? I'm saying, okay, this group has lower back pain, this group has lower back pain. This group is going to get strength training. Okay, this group is going to get flexibility training. I'm sorry, I'm left-handed and I'm writing on the mouse with my right hand. That says ST, that says FT. Okay, so if I run statistics and I say, okay, well, there is a difference between these groups, but I don't know what that difference is. Okay, that's what I'm saying. An effect size is like volume at a music, or volume of music at a party. So I'm saying there's a statistical significance between these groups, but I don't know how strong it is. So the effect size is going to tell me how loud the music is at the party. So is the effect size small, which we could say, okay, we're at a party and that means that the music is very low, or is the effect size very big, and that's saying that the music is very loud at the party, right? And if we look at this, we can kind of go back and say, okay, well, this group, there's not a lot of difference, so that volume's kind of low at the party, right? You can hear people talking, right? It's low. It's not much happening at that party. It's not bumping, right? But if I say, okay, well, there's a significant difference between these two groups, and it's detectable, it's a kind of a medium effect, well, that means now the volume at the party is turning up, right? Now I can't hear people talking because the music is starting to get loud. But if I find a large significant difference between two groups, well, that's like me cranking that music at the party, right? And now that party is bumping, right? People are having a good time. So it's kind of like there's this, we know that something is happening. I'm at a party. We know that there's music playing. I know something is happening, but I don't know the impact of that music on the party, right? The music could be low, the music could be moderate, right? Or the music could be super high. And that's what effect size is, right? And if we think about a party, if the music's low, people are just going to be chatting and talking, right? If the music's moderate, some people might be dancing, some people might be chatting. But if the music is very loud, well, that means the whole party's going to be bumping, everybody's going to be dancing, and that's an effect size. What is that music's effect on these people's behavior? And that's just kind of my analogy on it. So let me give you a couple of examples here. And I calculated some of these, and I'm just going to give you some examples of how this works in your world. So if I'm looking at physical therapy, and I do want to see if strength training versus controlled group for lower back pain. Okay, so I'm going to put a group through training. I'm going to let people not do anything, right? So I have group A, I have group B. Okay, group A is strength training, group B is not doing anything. So a physical therapist compares the effectiveness of a 6-week strength training program versus no strength training program, right? To see if this reduces lower back pain in patients. So group 1, here they are, group A, they go through strength training and their mean pain score is 3.5 and a standard deviation of 1.0. That's pretty good. Okay, so then I have, let's say I just kind of do this, right? I make my curve. Here's the mean score. Okay, control group or group 2, their mean pain score is 5, right? It's higher, and their standard deviation is greater. So that's a 1.2. So now this is what I do to calculate Cohen's, right? D equals group 1 and group 2. And it's divided by the pooled standard deviation. It looks like this. And then I get this score here, 1.36. Now let's go back. Where was that at? And I told you here that anything over a D value of 0.8 or higher is a pretty strong score. So if I go back over here and I look at this, well, 1.36, that's a pretty strong difference. That's a strong effect size. So this shows a large effect, indicating that strength training significantly reduced pain compared to the control group. So just to go back to my pictures, that would look like this. Let's say that's strength training, and let's say that this is control, right? And it's taking into consideration the mean and the standard deviation, right? So that would look like this. Here's the mean of the control. Here's the mean of the standard deviation. And it's saying that these values, there is a significant difference between these mean values that take into consideration the standard deviation. And it's saying that it is a pretty strong effect. So we ran our study, we collected data, we ran some statistical tests, we got a p-value, we go, okay, there is a difference, that's that music. Okay, there is music playing, but we don't know how strong that music is. So then you run your Cohen's d calculation and you find out, like, holy crap, there is a pretty significant impact or effect. So that music went really loud, and we know that there is a strong effect. And that gives us a lot of statistical power. So let's move to another one. So if we're talking about you sports psychologists here, and we're talking about mindfulness training versus no intervention in reducing pregame anxiety. So you're a sports psychologist, and you're comparing the impact of a 4-week mindfulness training program versus no intervention. And we're trying to reduce pregame anxiety in athletes. So let's say group 1. So here we go. I'll say group A. Right? This is the individuals that receive mindfulness training, and let's say they get a score of 15, a mean score, and a standard deviation of 4. Group 2, there's no intervention, and their mean anxiety score is much higher, and their standard deviation is greater. So we take that information, we run it through our calculation, and we find that there is an effect that is pretty strong. And why is that a strong effect? Because that value is greater than 0.8. So using Cohen-D's calculation, we find that there is, and again, I'll just say here's group A, let's say here's group B or group 1 and 2. Here's the mean value of the people that received the training. Here's the mean value with the standard deviation of the people that did not receive the training. And Cohen-D's tells us that the difference between those means are pretty strong. That's a pretty strong effect. And one more, I did not forget my exercise psychologist individual. So let's say we're looking at physical activity programs versus no programs for improving self-esteem in children. Well, let's say you're an exercise psychologist and you evaluate the effects of a 6-week physical activity program on self-esteem in children with disabilities. compared to a control group with no intervention? Well, the same thing. We collect that data. We find that the physical activity score, or the physical activity program, had a mean score of 70. That's pretty high, a standard deviation of 8. And group 2, who had no program, they had a lower self-esteem score. So theirs dropped and their standard deviation is greater. So we take that information, we plug it into our calculation, and we see that the Cohen's d tells us that there's a pretty strong effect, which therefore indicates a large effect size. And this means that the physical activity program had a significantly positive impact on self-esteem. So that is, let me just kind of go back and sum this all up. So when we're talking about statistical power, we want to have high levels of statistical power, which means we have to have a good sample size. The lower the sample size, the less power. We want to have a good effect size. The lower the effect size, the less power. And we want to have a p-value. And again, a p-value just tells us that something is happening, that there is a difference, but this effect size calculation will tell us how big of a difference it is. So essentially, it's like it allows us to kind of quantify the p-value. So that is statistical power, that is effect size, that is how effect size, sample size, and p-value are related. And now let's move into the discussion on an ANOVA. All right, so next let's introduce, well, it's not really introducing because I'm sure you've all heard of this and you probably know what it is, but we're going to talk about an ANOVA, or ANOVAs, which stands for Analysis of Variance. And ANOVA is like a really powerful statistical method used to compare the means of 3 or more groups. Okay, so in the last one, I was just kind of talking about 2 groups, but now we're talking about 3 or more groups. So this is a more technical and more complicated analysis or methodology of using statistical power. Pardon me. Sorry. And it's telling us if there are differences between the means of 3 or sometimes more groups to see if they differ significantly. So ANOVAs are used to compare the means of 3 or more groups. And the key components of this is there's something called the sum of squares that you might see in your papers, and this is a measurement of variation within the data. And then there's mean square, which is the average of these variations. And of course, I'm going to give you examples of this. So now, ANOVAs answer the questions, are there differences between group means large enough that they are unlikely to have happened by chance, right? So there's that chance thing again we're talking about. So it expands beyond a t-test, which only compares 2 groups, and it accommodates multiple comparisons in a single analysis. So let's take a look at a very, very basic example of this, just to kind of get our heads wrapped around it. So if I have 3 plots of trees, I have plot 1, I have plot 2, I have plot 3. Well, I could see that there are, of course, differences within each plot. So this would be group 1 or plot 1, group 2 or plot 2, group 3 or plot 3. So I want to see if there is any significant differences between these 3 groups of trees. And I have to consider that within each group of trees, there are also differences. So if I'm talking about this between group variation, this would be like the difference in average height of trees in the 3 separate plots. So you can see that in the 3 separate plots between group variation, I could see different tree sizes within each plot, right? And I kind of made this mean value right here, right? So here's the mean, right? Here's the mean. You guys all see that? And then I want to see is if there's variation within a group. So this would be like the difference in height of trees within each group. So obviously, this is very different than this. Obviously, this is very different than this. And this is very different than this. So by talking about trees, we are looking at, okay, there is variation between the three plots of trees, and there's also variation within each plot of trees, and that is what ANOVA is going to look at. It's going to look at three different groups and the variations between them and within them. So before we move into any sort of really complicated exploration of this, let's give some examples so I will not leave you hanging. So if we are talking about physical therapy and we're comparing rehabilitation techniques for knee injury, so I'm asking myself, which of the three rehabilitation techniques, strength training, flexibility training, or balance training, leads to the best improvement in knee mobility for patients recovering from ACL surgery? So I have three groups. I have my strength training, I have my flexibility training, and I have my balance training. So if I go back, right, let's talk about trees. Can't talk about trees too much, right? I have my strength training, mobility training, balance training. And within these three groups, I'm going to see variations in strength, right? Some people might get really strong. Some people might not gain much strength at all. Some people might get really flexible. Some people might not gain any flexibility at all. And if I look at, what was my other one? Balance. Some people might increase in balance. Some people might have a moderate increase in balance. And that's going to change the mean values of all of these groups that I'm looking at here, right? So if I have somebody really increase in strength and somebody not increase at all, well, the mean value of strength training is going to change. If I have somebody that surges in flexibility and then somebody else that doesn't really adapt to the flexibility training, that's going to change this mean value, which I'm comparing between this and this, right? And if I look at, what was the other one? What did I say? Flexibility? I forgot if I said flexibility or balance. Regardless, whatever my third training modality is, there's going to be variations within this training modality, which will change the mean, right? So this is what I'm looking at. So in this particular case, knee mobility measured in degrees of flexion before and after 12 weeks of rehabilitation, right? So that's what I'm looking at here. So I want to know which one is going to enhance knee mobility before and after 12 weeks of rehabilitation, right? So I'm going to have a pre, which is before. I'm going to have a post analysis, which is after. I'm going to have these three interventions, and I hope that my knee mobility is going to increase with all three of these interventions between pre and post, and I hope that one of these are going to increase more than the other two. So that's what we would run in ANOVA to determine which one is increasing knee mobility through this intervention, and we'll do a pre and a post measurement to determine that. So I have this here as well, so we could talk about the between group variation and the within group variation. So again, let's go back to trees, right? So plot 1, plot 2, plot 3, that's between group, right? Is there difference between this, and this? And within group, how big is the difference between the littlest tree and the biggest tree, right? We have all this variation here. And I just kind of made a quick little description about how we would look at this, right? So I have my balance, I have my strength, I have my flexibility, right? These are those three training methods we're going to use in ANOVA. And the difference between groups, right, between this, and this, the difference is in the average improvement in knee flexion between the groups. So I want to look at, for example, the strength training group may show an average increase of 20 degrees. The flexibility group may show an average increase of 15 degrees, and the balance group may show an average increase of 10 degrees. So the ANOVA will let us assess whether these differences are significant, or statistically significant. And it seems like strength training is going to win because it has this increase in about 20 degrees in knee mobility, right? So that is this group has a more significant change in knee mobility. Now within group, that's looking at all the people within this group, all the people within this group, and all the people within this group. And not every individual in the strength training group will improve by exactly 20 degrees. Some might improve by 10, others might improve by 30. The within group variation accounts for individual variation within the group. So let me just kind of go back here and let's just beat a dead horse, just so I know you guys understand it, and I know I'm doing my job at explaining this correctly, because when we're not calculating this and we're just kind of explaining how these things are used, it's a very different skill set. So again, I have strength training, I have flexibility training, I have balance training. It seems that the strength training has increased knee flexibility by 20 degrees, which was higher than the other two. So there's a significant difference in strength training. And then when we mentioned this within group variation, so if I go back here and I say, okay, these are all the strength training people, maybe this person improved by 30 degrees. Maybe this little guy here improved by 5 degrees. And maybe this one improved by 15 degrees, right? So I have to take in all this individual variation to get a mean value to compare against the mean values here and here. So that is how that works with, if we're talking about physical therapy. All right, and now we're going to move to our exercise psychologists, and we have a very similar scenario here. So I want to determine I want to compare mental imagery techniques for performance enhancement. And let's say I want to see which mental imagery technique is going to increase my performance in a 100-meter sprint over 8 weeks of practice. So I'm looking at 3 mental imagery techniques. I have visual, I have kinesthetic, and I have motivational, right? And visual is the athlete mentally visualizes success. Right? Kinesthetics is the athlete focuses on the feeling of physical performance or physical movement. Motivational would be the athletes imagine themselves overcoming all challenges. And I want to see which one of these best enhances this performance. So if I go back here, let me erase the trees, right? We're going from athletes to trees. It's not wanting to work. Maybe my computer's telling me it's done with trees. One more time here. It could be. Maybe it just doesn't want to deal with trees anymore. Oh, that's not working. Bizarre. Okay, so we'll just deal with it. So we have mental, we have, what did I say? I said visual, kinesthetic, and motivational. So we have visual, kinesthetic, and motivational. 3 different types of visual imagery to see which one increases my sprints. Well, if I do my assessment and I look at the between group variation and the within group variation, this is showing me the average performance improvement, right? So what was the average of visual? What was the average of kinesthetic, and what was the average of, what was my third one? Motivational, right? So what was the average here, average here, average here? Well, some people, let's say motivational. So let's say some people really responded well to motivational. Some people just had a little response, and then some people had a modest response. And let's say that is going to change my mean in this group. Same thing with the other 2 groups. The means are going to change by what? By the within group variation, right? So I'm going to have within group variation here, within group variation here, within group variation here. I got to get the means, and then I got to determine which one best improved my sprinting. And I have a little scenario here. So let's say the visual imagery group might reduce speed times by 0.05. That's pretty good. The other group might reduce it by 0.3, and the motivational group by 0.4. So this would suggest that the visual group responded best to the intervention and increased or decreased their sprint time. And again, within group variation, within each one of their group, not every athlete will improve at the same rate, right? Go back to trees, right? the rate of improvement. This one here improved substantially. This one here just had a little bit of an improvement. This one had a moderate improvement, right? So they're not all going to respond to the same intervention, but this will help kind of create some of the mean that we're looking at here, right? So some athletes in the visual imagery group may improve by 0.1 seconds, while others improve by 1 second, right? So there's going to be some differences within those groups. And let's do one more. I did not forget about my exercise psychology, folks. So let's say we're comparing exercise interventions to improve mental well-being in children with disabilities. And our research question is, which of the 3 exercise programs, aquatic therapy, there you go, they're swimming, they're having a good time, lots of smiles, we love smiles on children, adaptive yoga, right here, and seated strength training, right here, has the most significant effect on improving the mental well-being of children with physical disabilities. So the aquatic group is water-based exercise, adaptive yoga. Children participate in modified yoga poses and breathing exercises, and seated strength training. Children engage in upper body strength training exercises using seated positions. So we're measuring the mental well-being. And again, we go back to our trees. We have 3 different groups. We're going to have kids in this group that are going to respond a little bit, kids that are going to respond robustly in this group. Same thing here. We'll have a difference of responses and a difference of responses in the third group. And when we compare all those groups together, we'll see that there is a between group variation, right? So let's say, for example, the aquatic therapy group may report an average increase in 10% in well-being, while the adaptive yoga group increased 15%. That's pretty good. So, right, so these guys are leading the charge right now between those 3 groups. That's being determined by an ANOVA. And the seated strength training group may show only a 7% increase. So this one had kind of the worst effect, right? So it looks like if we compare in these 3 groups in an ANOVA, we can see that the adapted yoga had the most robust response and the most significant improvement in well-being between these 3 groups. And again, we're going to have some variations within how they responded to the intervention. And that is the basics of an ANOVA. So again, if you ever get kind of mixed up, just say, okay, he showed me trees, 3 groups. He said that there were significant differences between these 3 groups of trees, but also with inside, you're going to have different responses to an intervention. And that is the basics of an ANOVA. Now, it's important to understand, which I'm sure you already know this, but we're going to just beat a dead horse, that there are different types of ANOVAs. And the first one we're going to talk about is a one-way ANOVA. And for this conversation, we're really just going to kind of focus on one-way ANOVAs and two-way ANOVAs to start. And then as we get further into the semester, I'll introduce other ANOVAs. Most of the statistical courses that I took when I was at UIC as a student kind of stopped at a two-way repeated measure ANOVA, because that just kind of seemed to be the extent of tools we had for translational research. So I will continue to go on and present more of these to you with inferential data. But today I'm going to stop not at a two-way repeated measure ANOVA, but just at a two-way ANOVA, just because, you can only listen to so much statistics before it becomes diabolical and painful. So let's talk about what the major differences are between a one-way ANOVA and a two-way ANOVA. All right, so we talked about what an ANOVA is. It's an analysis of variance, and we, of course, talked about different type of variance, between groups or within group variance. I think we kind of beat that one into the ground. So now we're talking about a one-way ANOVA, and this is used when we have basically one independent variable with multiple groups or multiple levels. So for example, if we're studying the effects on 3 different training programs, like we did before, right? We were talking about yoga, we were talking about seated chair exercises, and we were talking about aquatic sports. And let's say we're testing those on the mental health of individuals with disabilities. Well, a one-way ANOVA would help us determine if there is a significant difference between the program. So we've kind of already talked about that. So the key points of a one-way ANOVA is it looks at one factor, okay? In what I told you guys previously, it was looking at the types of training. It can handle 3 or more groups, and it tells you if at least one group is different, but you need additional tests like a post hoc test to find out which group is different. So we talked about, somebody mentioned in one of our Lit Circle lectures that someone conducted a post hoc test and they didn't really know what it was used for. So if we're doing this one-way ANOVA, let's go back to this one because this was the last one we talked about. We're looking at a single, well, let me go back to this one. Sorry. We are looking at a single variable exercise programs between 1, 2, 3 groups. That is the variable, and we're trying to determine which one of these has a significant impact on mental wellness. Well, in order to determine which one is more significant, we have to do a post hoc test that will identify a clear winner. I'm not going to go into that. I just want you to know what it is. A post hoc test tells us it's just kind of like an effect size, right? It kind of quantifies which one of these training programs are most significantly different. And that's all I really want you to know. It's just telling us which groups differ. So we could also think about this as, let's say we're doing schools and we're looking at test scores. Let's say I have school A, I have school B, I have school C, right? A, B, and C. And I am looking at one factor. I am looking at test scores. Well, I would run a one-way ANOVA that is looking at test scores, and test scores. It's going to identify between group variance and within group variance. I am going to have to run a post hoc test, and it will tell me which school has the better test scores. And same thing here with trees, right? I keep bringing the trees back here, right? If I want to know which tree is bigger, right? I have tree 1, tree 2, tree 3, and I want to say, like, let's say what tree grows most over the course of a year. I have to look at tree 1, tree 2, and tree 3. I would have to run an ANOVA using, the changes in height, whether it's in feet or centimeters, and I would determine which tree grows most significantly over the course of a year. So if I'm looking at growth as my variable, that's what an ANOVA, a one-way, does. So again, that's why I have this here. Think of it as comparing the heights of different trees in 3 separate gardens or over a different time frame, right? A one-way refers to the fact that you are comparing one characteristic, which in this case is height, across different groups, which could be gardens or seasons. So that is what a one-way ANOVA does, and I gave you that with all of these examples. These are examples of one-way ANOVAs, so I tried to set that up for you so you're like, oh, that's what he just talked about. That's a one-way ANOVA, right? So that makes perfect sense. And let's, of course, give us a slightly more in-depth look at a one-way ANOVA. So we're comparing the effectiveness of 3 physical therapy approaches on lower back pain relief. Okay, so we're looking at research question. Which of the 3 physical therapy treatments, manual, exercise, or electrical, leads to the most significant reduction in back pain in patients after 8 weeks? So I have my 1, 2, 3. There are 3 groups. I'm looking at one variable, which is what type of therapy. And let's say pain reduction is measured on a standard 0 to 10 pain scale after 8 weeks of therapy. Well, if I go over here and I take a look at this, okay, a one-way ANOVA, is appropriate here because there are 3 independent variables, right? Which we're talking about this type of physical therapy. And it's presented in 3 levels, right? Manual therapy, exercise therapy, electrical therapy. And we're comparing these groups to pain reduction, right? So we'll get a between group variation and within group variation. And we kind of know what that is. So you can look at these and read this on your own. I'm just showing you a more in-depth variation of this. Same thing is true for my sports psychology folks. If I'm doing a one-way ANOVA and I'm comparing the effectiveness of 3 mental training techniques on athletic performance anxiety, which of the 3 mental training techniques, mindfulness meditation, goal setting, or visualization, is most effective in reducing performance anxiety in athletes? Well, here's my 3 groups, right? What am I measuring? I'm measuring performance anxiety to see which of these 3 groups is impacting this variable. I'm doing it across 6 weeks. And here's an explanation of what that one-way ANOVA does, right? We would use this one-way ANOVA because there is one independent variable, right? We're talking about we're talking about an independent variable, which is mental training techniques, right? This is the independent variable. There are 3 levels to this: mindfulness, goal setting, visualization, and we're comparing these groups on one dependent variable, which is this anxiety reduction. So if we go back here, we're talking about anxiety. We're trying to reduce this, and there's 3 groups that we're using to see which one of these are going to reduce this. Okay, you guys can look at this at your own time because I've been kind of measuring or telling you the same thing for the last 20 minutes, and this is just here for you if you want to read it. And I'm not going to forget about my exercise psychology folks. So if we're comparing the effectiveness of 3 intervention techniques on mood improvement in disabled children, well, what am I looking at? I'm looking at mood levels, and I have 3 groups which we're going to apply to see how that impacts my mood levels. So I have a structural physical activity group, I have an expressive arts therapy group, I have a social skills training group. There are my 3 groups, and I'm going to see which one of these impacts this more greatly. I will run the study, I will collect the data, I will run an ANOVA. Once I get the ANOVA, I will run a post hoc test, and that will tell me that, oh, maybe it is this group that is having the greatest impact on mood improvement, and therefore that is the group that is most significant. And here we go, there's that explanation there. You can have at it as much as you need to. Now, because I spent so much time talking about a one-way ANOVA, now I want to look at a two-way ANOVA, which we haven't really touched on yet. So let's talk about what a two-way ANOVA is, and you probably already know what this is, but you know I'm going to provide you with lots of details and beat lots of dead horses and make sure that you understand this and this really sticks with you. Is a statistical method that serves a crucial role in understanding the effects of 2 independent variables on a single dependent variable. So remember, when we talked about a one-way ANOVA, we talked about a single effect on a single variable, right? So we talked about ANOVA so far, we talked about a one-way, but now we're talking about a two-way. And a two-way, once again, is a test that determines the effects of 2, that's why it says two-way ANOVA, right? Let me get yellow. 2 independent variables, I'm going to say 2IV, on a single dependent variable, on one dependent variable. So what does that mean? Well, let's talk about this for a second. So if I have 2 independent variables, let's say I'm looking at a type of exercise, and let's say, well, let's get a color that works here. Let's get green. Let's say I want to look at the type of exercise, right? Which in this case could be strength training versus yoga training, right? And the time of exercise I need, let's say 60 minutes to 90 minutes, and I want to see how these two independent variables impact stress levels, that would be the dependent variable. Well, this is an example of why we would use a two-way ANOVA. I want to see if strength training or yoga has a greater impact on stress levels, and I want to see if 60 minutes of one of these or 90 minutes of one of these has a greater impact on stress levels. So things get a bit more complicated with a two-way ANOVA. And don't get this confused with the two-way repeated measure ANOVA, because that makes things even more complicated. So we'll get into this in detail. So we're talking about the ANOVAs, the analysis of variance. We've talked about a one-way. Now we're talking about a two-way. Well, let's get into the specifics of this particular type of method of research. So a two-way ANOVA, which again is an analysis of variance, is a statistical test used to determine whether there is any statistical significance or differences between the means of three or more independent or unrelated groups. Okay, so and I just kind of showed you that, right? So we're looking at these differences in three or more groups, and we're evaluating the effect of two independent variables on a dependent variable. And the purpose of this is it tests for interactions between two independent variables, right? So if I'm looking at type of exercise or time of exercise and how this impacts stress levels, well, this obviously is a test for interaction between two independent variables. Are these things impacting stress levels independently? Is there an interaction between these things? Does time play a role in these things? There would be another independent variable. So we're looking at how all these factors impact a single dependent variable. And I will, of course, give you guys lots of examples of this. Yeah, let's move on to the next section here. So why is this not working? There we go. Okay. We use a two-way ANOVA, not a repeated measures ANOVA. That's a different test when we have two independent variables and we want to assess their effects on a dependent variable with each group or observation belonging to one level of each independent variable. And I know that gets confusing, and we will talk about what that means in a moment. Again, like I said, when I'm looking through the textbooks, I realize that statisticians are writing this, and sometimes it's like I have no idea what that means, okay? This design is suitable when the groups being compared are independent from one another, meaning different participants are used in different groups. Okay, so what does that mean? Well, let me give you an example of this. So let's say I'm using a two-way ANOVA and I'm studying the effect of diet and exercise on weight loss, right? So independent variable 1, independent variable 2, and which one is impacting the dependent variable most? Are they both doing it? Are they individually doing it? Now, when I said back here, where's that at? Which one was really confusing? I think it was this one here. Effects. Okay, here. Belonging to one level of each independent variable. Well, what the hell does that mean? Well, that means if I'm looking at diet, well, diet has a couple of levels here. We have low fat, we have low carb, we have Mediterranean. So which one of these levels within this independent variable are more advantageous to weight loss? Well, then if I look at exercise type has two levels, right? Cardio and strength training. Is there a combination of low fat and strength training, which has a greater impact on weight loss? Or maybe it's cardio and Mediterranean that has a greater loss on impact. So it's looking at all of these levels within the independent variables, and it's determining whether or not these things are impacting weight loss. So in this example, different participants are placed in groups based upon their diet and exercise, right? Each group has a unique combination, right? So I have 3 groups. I have 1, 2, 3. That's why I'm doing an ANOVA. Each group has a unique combination. So let's say this first group has low fat plus cardio, right? So this would be low fat plus cardio. We have Mediterranean and strength training. So let's say we have Mediterranean plus strength. Oh, that looks like an S. And then we might have a third one, which is just low carb and no exercise, right? And we'll say no exercise. Well, now I have 3 groups. And which one of these 3 groups with different independent variables and different levels are going to impact weight loss? I hope that makes sense. So I'm definitely trying to take what is in the textbook and I'm trying to make it our own kind of interpretation of it. So again, just understand the basics. We have a statistical method where we're measuring the effect of 2 independent variables. Those independent variables can have different levels, and I'll show you what that is in a minute. And we're looking to see how that impacts a dependent variable. And a one-way ANOVA was a little easier because we only had 1 independent variable, right? So this is testing for interactions between 2 or more independent variables. Well, that's what we saw here. We saw a couple of interactions between these independent variables, right? We took one from diet and we put one from exercise. So we took low fat and cardio. Here, let me clean this up and just make it a little more understandable here. I'll do it by color, right? We'll do it by color coordination. So again, I have 2 independent variables. Let's highlight. I have 2 independent variables, right? Diet and exercise. Within these independent variables, I have different levels and I'm doing different combinations. So let's say I do low fat and I said cardio. So that's one group. That's this group here, low fat and cardio. Okay. And then I do another group. Let's highlight this in green. I do Mediterranean and strength. And that's this group right here, right? Mediterranean and strength. And then I do a third group, which we will do, let's do light blue, low carb and no exercise, right? So that would be this group right here. 3 groups, 3 different combinations of independent variables. And I'm going to see which one of these has the greatest impact on, let's do purple, on weight loss. All right. So that is why we would use a 2-way ANOVA. It tests for interactions between 2 or more independent variables, and we are basically running this test between 3 or more groups. So let me give you an example. And again, we don't need to calculate it. We just need to understand why the researchers are using it. So let's go to my physical therapists out there. So my research question: does the type of rehabilitation method, independent variable 1, and frequency, independent variable 2, affect improvements in mobility, right? So we're looking is which one of these independent variables has the best improvement in mobility. So this would be my study design. We've just given you an example of what you might see. Independent variable 1, we're looking at rehabilitation method, right? This one right here. Independent variable 1, rehabilitation method, and there are 3 levels: strength training, balance training, stretch focused rehabilitation. Independent variable 2, frequency. I'm looking at therapy session frequency, and in this one I only have 2 levels, right? I have 2 sessions per week, and then I have 4 sessions per week, right? So now I could make a variation of these different groups, right? I could have group 1, I'll do it by color. Group 1, which is, let's do green, strength training, 2 sessions per week. I could do group 2, which is balance training, 4 sessions per week, right? I could do group 3, and you could have any variation of this. stretching, focus, rehabilitation, and we can also do that 2 times per week, right? And we can create 3 or more groups based upon these different independent variations, right? We can make multiple variations, and we're going to say which one best improves mobility, right? So that would be an example. So we're looking at range of motion. Which one after 12 weeks has the most improvement in mobility? So if I move to my next section and I look at my sports psychologists out there, I'm just giving you examples. You guys are reading the papers, not me. So I'm just trying to show you what they're doing in these statistics in case you're struggling with trying to understand them. If I look at does the type of mental skills training, and that's independent variable 1, and level of competition, independent variable 2, affect an athlete's performance anxiety levels. So now I'm looking at this dependent variable, okay? Now I have my independent variable 1, which we said was mental skills training. This one has 3 different levels. We have relaxation training, visual training, goal setting training, right? So I can make different variations of these trainings with my second independent variable, which is level of competition. Amateur athletes, semi-pro athletes, professional athletes, right? This is like, it's like going to a buffet, right? I can get my plate and mix and match. And I can create 3 or more groups based upon these different independent variables to see which combination, 1, 2, or 3, right? Which combination of these independent variables best reduce anxiety levels, right? So we can look at maybe in this particular case, if we're doing this study, maybe the combination of goal setting training in professional athletes has the highest level of impact on anxiety levels. So maybe that is the combination that a 2-way ANOVA will show. And then lastly, for my exercise psychologists, we're looking at types of physical activity program, independent variable 1, and the level of social support, independent variable 2, which I have a picture here, right? We have lots of social support. And how did this affect physical fitness levels, our dependent variable? And again, I have my independent variable 1, which is physical activity programming. I have several different levels, right? I have structured, I have play-based, I have aquatic, right? All of these are going to have different impacts on physical fitness levels. And my independent variable 2 would be social support. So I could have low social support, I could have moderate social support, I could have high social support, right? So I could make groups in my research. You know, let's say I have 3 groups. And within those 3 groups, I have different variations of these independent variables to see how they impact physical fitness levels. And this is what that 2-way ANOVA would look at. It's looking at the interaction between these different types of combinations of independent variables on the dependent variable. Now, like I said, I am trying to keep this as brief as I possibly can because I know listening to 40 minutes of statistics is painful. That is why I'm trying to make these slides relevant to your specific sciences. So I hope it's helping. I hope you're like, okay, well, I did kind of learn something new. He's not just telling me things that I didn't know about. And like I said, some of you folks are brand new to research and you've never had any explanation of what these things are. And that's why I'm trying to explain it in this manner. So that when you're reading it in the paper, you're like, well, what the hell is a 2-way ANOVA? Oh, you're like, oh, he did that presentation on it, and he said something about 2 independent variables. Oh, I understand what they did and why they did that. That's all we're doing this for. So I hope that was helpful. I will see you guys very soon, and I will be back again within the next lecture to talk about the differences between a 1-way ANOVA, a 2-way ANOVA, and a 2-way repeated measure ANOVA. And these statistics are just going to get more complicated. So I hope that was helpful. You guys have a fantastic day, and I will see you very, very soon.